Hello, I'd like to welcome you to the Developing Low-Pass Systems with Lattice Avant Mid-Range FPGAs session of the 2024 Lattice Developers Conference. So before we dive into the presentation, just a little bit about myself. My name is Gordon Hands. I'm Senior Director of Product Marketing here at Lattice Semiconductor, where I've spent over 20 years defining and launching small and mid-range FPGAs. Prior to joining Lattice, I did my Master's in Business Administration at Arizona State University, and prior to that, I did my Bachelor's in Engineering, in Electrical and Electronic Engineering at the University of Birmingham in the UK. So what's on the agenda for the breakout session today? I'm going to start out by doing a quick review of the edge to cloud application space, the most common application space for mid-range FPGAs. I'll do a quick review of the Lattice Avant platform, and then I'm going to go into 3 different application examples that I've chosen because they both illustrate the low-pass capability of the Avant platform, and also because they give some tips and tricks as to how you can get the best out of these products to deliver the lowest power designs for your application. So I wanted to start out by giving an overview of the edge to cloud application space because as we were defining and developing the Avant platform, this is an application space we had in the forefront of our minds. It's one of the most common uses of mid-range FPGAs. And on the slide, I kind of spell out 3 of the most common edge to cloud application functions that we see. I show robotics, wireless, and camera. And then for each of these, I'm showing the acquisition system, whether it's precision sensors, high-speed ADCs, or video sensors, how that data is pre-processed and aggregated, the connectivity that's required to talk to the rest of the system, and then lastly, the kind of computing and data orchestration that's required within the system. So as we think about the edge to cloud application space, one of the things that we see is there's increasing demands being placed on the FPGAs in those systems. Really 3 of the demands that are being placed on the FPGAs are themes of the developers conference this year. There's the how do we embed artificial intelligence at the edge. There's the area of how do we enhance the connectivity between the edge and the cloud. And then lastly, how do we make sure that the systems that we're deploying in this space have the resilient security that our users desire. So as you folks, the FPGA developers, are trying to take mid-range FPGAs and develop solutions that address some of the themes and drivers I showed on the last slide: edge AI, improved connectivity, and more resilient security. We're very aware that you need to do that within tight thermal budgets or tight thermal constraints. We see those constraints being placed on systems due to a number of factors. It could be that it's a portable system, or maybe it's an autonomous system. Could be that there's a lot of pressure on system cost or operating cost. And we understand that by driving down power consumption, we can very much help you address some of those constraints, enable the delivery of products in small enclosures, keep the temperature within the product down so that you don't disturb sensors, increase the amount of runtime for rechargeable units. We can help save cost by limiting the use of active cooling, and by keeping overall system temperatures low we can improve reliability. So as we developed the Avant platform, we very much had in mind this edge to cloud application space. We went and sought inputs from developers across a wide variety of applications in order to shape the definition of the product. And three big themes came out of those conversations. The first one is we heard developers saying, hey, we need help reducing power consumption. And we're very proud that as we've been rolling out the Lattice Avant platform, we've been able to demonstrate up to 2.5 times lower power than relevant competitive FPGAs. We also heard that there's a need for faster connectivity. So we incorporated within the Avant platform 25 gigabit per second Ethernet capability. And then lastly, we heard there's continued pressure on the form factor of your equipment. So we're very pleased to have been able to launch a platform that delivers up to 6 times smaller package size or form factor than similar relevant competitive FPGA devices. So let's take a quick tour around the Lattice Avant platform. At the center of every Lattice Avant device, shown by the large gold block in the center of the diagram, we have a low-power FPGA fabric. In addition to supporting low-power logic implementation, the fabric has plentiful embedded memory blocks and DSPs, which incorporate the ability to support optimized 8x8 multiplication, a kind of multiplication needed by many of the AI algorithms people are trying to implement at the edge. If we look along the bottom of the chip, and in the upper right-hand corner, we have our programmable IOs supporting all of the normal LV-CMOS levels that designers are looking for. The MIPI up to 1.8 gigabits a second, LVDS up to 1.6 gigabits per second, and then a variety of other standards such as I3C, SGMII, and 7-to-1 LVDS. In the upper left of the chip, we have the high-speed SERDES interface supporting the very popular PCI interface up to generation 4, 25 gigabit Ethernet, and a whole variety of other standards. And then lastly, in the upper right of the chip, we also have the security block. The security block enables protection of the chip and the design within it, keeping your design and your system secure. So to date, we've made available 3 different families based on the Avant platform. Avant E, which is optimized for edge processing applications with high-speed DDR memory support, coupled with the high-speed flexible IOs on the Avant platform, supporting things like 1.8 megabits per second MIPI, and the bitstream security so that you can feel confident in the authenticity and security of the bitstream or configuration within the device. Then we have the Avant G, which is really designed as a general purpose mid-range FPGA supporting up to 12.5 gigabits per second SERDES. So this has all of the capabilities that we had on the Avant E, but adds that 12.5 gigabits per second SERDES to enable support for things like PCIe up to Gen 3 and 10 gigabits per second Ethernet. And then lastly, we have the Avant X, which we think of as the extra speed version, supporting up to 25 gigabits per second SERDES. So you get all of the capabilities that were in the Avant G, plus a 25 gigabits per second SERDES supporting PCIe up to Gen 4 and 25 gigabits per second Ethernet. We also incorporate within this device some additional security features that allow the user logic to make API calls to a security engine for things like encrypting data within the system and on the move as it's transmitted to and from the device. So far we've talked about edge to cloud as an application, and we've also talked about the importance of low power in that application space, and how Lattice, as we were defining the Avant platform, took inputs from developers such as yourselves in order to define the product and kind of guide its development. So now I want to make things a little bit more real by looking at 3 very specific examples. The first example that I want to look at is in the space of AI processing. And what we're doing in this example is taking a neural network that's been defined for an automotive application. It takes an input video stream and then looks for vehicles within that stream, places a bounding box around those vehicles, and then sends an output stream from the device. And we were interested to investigate how does the Lattice Avant solution compare with other similar solutions from other FPGA manufacturers, using the kind of FPGA that we would recommend and the FPGA that those manufacturers would recommend. So we did some work with one of our partners, Soft Nordics. We took the neural network that we defined for this application. We implemented it on the Lattice device and 2 competitive devices. And as we go through the next few slides, I'll share out the results that we got from that investigation. So before I dive into the results, I want to talk a little bit about the model and how we trained it. So in terms of the model, we built a model that uses a mobile net backbone, and we combine that with a YOLO-style detection head. In terms of the data we're feeding into the model, it's 480 by 288 pixels, and the model is set up to categorize 2 kinds of objects, cars and people. And we built the model using 8-bit integer for both the activations and the weights. This is a fairly common optimization for edge AI. In terms of training the model, we utilized the BDD 100K dataset. It's a dataset for driving type applications. We used about 38,000 images from that data set, and then using AI type techniques, we expanded or augmented that data set to 700,000 images. So we're interested to see how the model that I talked about on the prior slide would behave when we went ahead and implemented it on hardware, FPGA hardware from various competitors. So we selected hardware that was available, had a development board, was recommended for AI, and we landed on the Zinc UltraScale Plus devices from AMD and the Aria 10 SX devices from Intel. What you can see in the results table is we were able to successfully implement the network on the Lattice hardware at 70 frames per second. And when we did that, we saw that the power consumption, as we measured on the hardware, was 1.3 watts. Then when we looked at the Zinc devices, we chose to operate the network within the Zinc device at a similar kind of frames per second, just actually a little bit more, 79 frames per second. And when we went ahead and measured the power consumption, and again, this is on the hardware, we saw that the power consumption was 4.2 watts. And then lastly, when we looked at the same function and we implemented it using the Intel Aria 10 SX devices, there we were not able to achieve the same level of performance. We were able to achieve 6 frames per second, and we saw that their power consumption was 14.2 watts. So we think that this data set kind of gives a good illustration of how we've really optimized the Lattice Avant platform for doing low power processing at the edge, as the graph on the left-hand side shows, up to 13 times lower power than the competitive devices. So let's move on to application 2 of the 3 applications that I wanted to share out today. So the second application that I chose is the small form factor plus pluggable modules. I chose this because I think it really embodies a lot of what people are trying to achieve in edge to cloud connectivity. So for those people that are not aware, the SFP Plus module is a small pluggable module that gets used in applications such as networking and compute to allow a variety of input standards to be connected to a single standardized piece of hardware, whether it be a switch or a server. And we're seeing a lot of interest from our customer base into using FPGAs for this application. People want to use FPGAs because of the flexibility, and they want to use that flexibility to implement functions such as traffic monitoring and security. But the application comes with its quite a good set of challenges. So first, it's a very small form factor application. We see that the dimensions of the module are 11 by 13 by 56. And we also see that these modules have very tight power budgets. So there's a variety of different levels that are defined. In our customer base, we're seeing a lot of the customers trying to achieve level 2 operation, which requires that you keep the overall power consumption below 1.5 watts. So let's take a little bit more of a look into this application space. Let's talk a little bit about the application that we chose to implement for this 10 gig SFP Plus example. So in this particular application, we wanted to take a 10 gigabit Ethernet stream in, feed that through the Lattice Avant G30 device, which comes in a 11 by 9 millimeter package, so a good package to put within one of these space constrained modules. And then we wanted to drive data out into the system over 3 1 gigabit per second Ethernet lanes. For this particular application, we chose to implement both the 10 gigabit Ethernet and the 1 gigabit Ethernet using our SERDES block with its hardened PMA and PCS layers. We did that because that was the lowest latency implementation, although it's worth noting that we can also implement the 1 gigabit Ethernet over LVDS-IO using the SGMII interface if lower power was desired. The functionality that sat within the FPGA basically utilized 60,000 4-input lookup tables, about 7K registers. We had 50 GPIO in the overall design, and we made use of 17K bit of the embedded SRAM. So on this slide, I share out the results from the Lattice Power Calculator for the particular design that we've been talking about, and how they compare to that 1.5 watt level 2 limit. So we're sharing the results at 25, 40, 55, and 70 ambient. And then for interest, I split the data between the static power that the FPGA consumes, the dynamic power, the power consumed by the logic and fabric, and then the power that's consumed by the SERDES. And what we can see is at each of these 4 temperatures, we're able to stay below the 1.5 watt limit that's required of the application. So let's move to the third and final application that I'm going to be going through in this presentation. What I'm going to be talking about in this application is how we can optimize power consumption for edge monitoring by combining fast configuration and low power. So what we observe as we engage with our customers is many common edge monitoring applications require processing at a rate of about once per second. And in fact, we've had a lot of experience implementing these kind of functions in client compute platforms for human presence detect. And there, we really enable a much lower power solution for our users by gating the FPGA on and off, making use of its fast boot time and low power to deliver the ultimate in low power for our users. So we observe that there are multiple similar applications in other markets, industrial, automotive, and others. You know, some of the applications include security monitoring, collision avoidance, operating monitoring. So we said, well, what would happen if we took the Avant platform that's really intended as that edge FPGA and made use of its fast boot and low power to deliver a further optimized power solution into the market. So let me go through that in the next few slides. So let's take a look at this concept of combining a low power FPGA and fast boot to achieve even lower power in a little bit more detail. So let's start out by looking at the orange line on the chart. So what you'll notice is, you know, for most of the time period, the power consumption is 300 milliwatts. This represents the kind of static or background power of the FPGA that we chose for this application. And what you'll also see is 2 times a second for about 50 milliseconds, we're doing some processing. So the dynamic power associated with that processing is about 100 milliwatts, and the total power during those periods of processing about 400 milliwatts. So when we kind of average that out over 2 seconds, we see that the power consumption, a little bit over 300 milliwatts. But you don't need to leave the FPGA turned on for all of that time. We can make use of the fast boot and power gating the FPGA to further reduce the power consumption. So if you take a look at the green line, what you see is at time 0, I start to configure the FPGA. It takes about 20 milliseconds in this case. What we see is the power drawn during configuration is about the same as static. So we're consuming about 300 milliwatts during configuration. Once we're configured, we do our processing task. So that's about 50 milliseconds. We're consuming about 400 milliwatts. And then as soon as we're finished processing, we power gate off the FPGA, sitting there drawing no power. And then right around the half-second mark, we start to configure the FPGA again, 20 milliseconds at 300 milliwatts. We do our processing, 50 milliseconds at 400 milliwatts, and then we go to sleep. So the average power in this second case is about 50 milliwatts. So by combining power gating and fast boot with the low power FPGA fabric, we're able to achieve a further reduction in power consumption, in this case of about 6x. Okay, so let's wrap up the presentation. So we started the presentation by talking about edge to cloud connectivity as a very common application space for mid-range FPGAs. And we talked about how Lattice, as we were defining the Avant platform, listened to developers such as yourselves to make sure that we were developing a product that was going to be a good fit for those kind of applications, and really provide a solution that can be used for sensor aggregation, processing, and connectivity in that space. We talked about how the Lattice Avant solves power and thermal challenges in that environment. And we did that by looking at 3 different application examples. So the first application example we looked at was AI processing at the edge, where we took a function and compared what the power consumption was in Lattice and 2 other competitive FPGAs. What we saw is that the Lattice devices can deliver up to a 13x power reduction as compared to the competitive devices that we looked at. We then took a look at SFP plus pluggable modules as a kind of very typical example of some of the power and space constraints that we often see in edge connectivity. And we showed how the Avant product, the G30, can meet both the tight form factor constraints and the thermals needed in that application. And then we wrapped up by talking about how we can combine the fast boot and the low power to drive overall power consumption even lower. And what we showed is by power cycling the FPGA, we can reduce the already low power consumption by a factor of 6x for even lower power in your designs. So I hope you found the breakout session informative. And we're now going to switch to a section and kind of go through some of the common questions that I get asked when I'm presenting this kind of material. So jumping into the frequently asked questions. The first one is, and perhaps the most common, how does Lattice Avant achieve its low power? So at Lattice, we always like to think about, there are kind of 3 areas which we focus on in terms of driving a lower power within the devices. The first is the architecture. So for instance, in Avant, we chose to use the LUT4 as the logical element because LUT4 is very proven to deliver power and area optimization. Then there's circuit techniques we use as we're developing each of the circuit blocks to make sure that they deliver the best power possible. And then lastly, there are things that we can do at the process level that help further reduce power consumption. So because we spend a lot of time talking about power and form factor, we often get questions about, well, what are some of the other features and capabilities that Lattice Avant provides? So you really get all of the kind of capabilities that you might expect in a modern mid-range FPGA. All of the flexibility and capabilities in terms of IOs. With some advances not offered by all of the competition, such as support for LPDDR4. You get the SERDES that we talked about in the presentation, and support for the most common SERDES standards that we see out there. I touched just very briefly, but you get industry-leading security, and then of course form factor and boot time we already talked about. Another question we often get is, how fast is the FPGA fabric in Lattice Avant? So this is kind of a really good question because we all know that to some extent power and performance can trade off against each other. So as we were defining the Avant product, we spent a lot of time trying to understand, how much performance do people really need in their designs? And what we discovered is, by talking to all of you folks, that if we can operate at 350 megahertz, we meet the vast majority of applications that are out there. And by optimizing our chip to operate up to 350 megahertz, we can get further power reductions rather than needlessly chasing for higher performance. How does Lattice Avant achieve fast boot up? So this is kind of a great question. I think people look at what we're doing and say, wow, like up to 10x faster boot than some of the comparable FPGAs. How do you guys do that? And it's really just by paying attention to every aspect of the boot process. So for instance, the internal oscillator frequency. Is it high enough? Do we control the tolerance well enough so we don't needlessly give away performance? Do we support octal SPI or just the older SPI memories like by 1 or quad by 4 SPI memory? Have we paid attention to how quickly we start downloading from the SPI memory after power good is achieved? So it's really by paying attention to all of these factors and more that we're able to deliver the fast boot that we talk about. What inspired the combination of fast boot and low power? So originally we were kind of inspired because, as I mentioned earlier in the presentation, we were working in the client compute space, right? So that's another way of saying the laptop space. And I think most people know in laptop power consumption is very critical. Want to keep the power down so the battery life is good. And in order to achieve that, it became obvious that we wanted to power cycle the FPGA to turn the FPGA on and off so that it's only on when it's needed to perform a function. So having seen how helpful that was in the client compute space, we said, why don't we take that application and apply it into application spaces such as automotive, where we've got some really fun things happening in terms of automotive security, and industrial, where we think that it can add a lot of benefit in terms of operator monitoring and safety, while still keeping the power consumption as low as possible. Question, what other low power options does Lattice provide? So I think as a company, if you look at our kind of tagline, it's low power programmable leader. So most of the products that we do have kind of an emphasis on low power. I think if you're interested in looking at other classes of devices, in the small space, take a look at our Nexus platform that delivers solutions between about 10K LCs and 100K LCs that have industry-leading power. If you want to look at some devices that are below 10K LCs, the Mach XO3 family would be a great place to start. And then lastly, where can I learn some more? So I just want to encourage everyone that has some interest in what we've presented today, just go check us out at our website, latticesemi.com. So that's latticesemi.com. Hope to see you there and that you find the information that you're looking for. All right, with that, once again, big thanks for the attention. Hope you found the material useful and informative, and we'll catch you next time.